Hello everyone. Today I will explain to you about the multi-cluster monitoring project and how it came across in line, how it helped us during major outages, and how it made us keep a track of what's going right and what's going wrong in our production system. The agenda of our presentation today includes a bit about line in its infrastructure and the various issues which we faced in line. Then a bit about the multi-cluster monitoring project, its overview, the matrix which we used in the project and its architecture, and finally how we utilize the cluster monitoring project to troubleshoot the production cluster or identify the different metrics and the trend or the behavior of our cluster. Now, line as its ecosystem here is represented includes not only messaging but also payments, games, news, the Macan as a food delivery system, live streaming, and a lot of other things. There are a total of 193 million users globally offline with almost nearly 4.9 billion daily messages. There are at a time 92 million, not at a time, means in a month, there are 92 million users in Japan who are using Line, and Line as a company has a total employee strength of more than 9,200 employees. A bit about the Line's infrastructure and its scale. So there are almost around 6,500 hypervisors in Line, 94,000 plus virtual machines, and more than 68,000 physical machines, which are incorporated in the Line's production cluster. Now, with this large scale comes a lot of responsibilities and problems as well. Some of the issues which we faced in line when handling such a large scale where the first one was the lack of resource failure awareness. What it means basically is that if a resource failed in any particular area, for example, if a VM was not getting created or a particular user resource uh, went into an error state, or maybe the dashboard which the user is checking it out, they are not able to access it, or the developer reports some issues, for example, a volume is not getting mounted, or some other things like a messaging queue facing an outage, or a high CPU, high memory resource usage. All of these are basic problems which comes uh, in the day-to-day operation of a large production cluster. But if we don't monitor these resources properly, we will not be able to we may not be able to get that information ahead of time. What that means basically is that if a resource fails and it's a user facing resource, then it's a bigger problem than if we get the right information ahead of time before the user sees it. The second is the lack of production cluster status awareness. This basically means is that we did not earlier have proper information about how a cluster is basically basically functioning. What it means is that the API response time, the API success rate, how how the requests which the user are sending are responding, how long does it take to create a resource, to delete a resource in a day, within a week, or in a month. Those type of information which give us which give us an image of how the cluster is basically functioning. We did not have that. All these data points are already available in the system, but what matters is that we collect them and we see the data, analyze the data, find a pattern, and then make a make a human understandable system out of it. That was missing. And the final point which was missing was there was no particular service level indicator. Again, going back that there is data everywhere, but we have to make a meaning out of it. And from that meaningful data only, we will get the service level indicators and service level objectives. These all things led to the multi-cluster monitoring project. So the lack of resource failure awareness gave us the points that we should collect data, that we should collect proper data. We should calculate this data as a matrix and visualize it on a dashboard so that it's easier for a human to make sense out of it. The lack of production cluster status awareness, it gave the rise to make a trend data visible and to showcase the actual cluster capacity. What this means is that if we want to see the behavior of a particular cluster, we need to get that the particular API request response time, for example, over a long period of time, like let's say a week or a month or maybe 2 or 3 months, and see the average out of it. Based on the average of every month or every week, we can make a proper diagnosis. We can understand whether our system is functioning properly, or whether there is some problem in the scheduling algorithms or in the backend, or whether there is an improvement based on some other bug fixes which we have done in the recent past. And finally, the lack of definition to ensure performance platform availability. For this, we defined SLO, and we defined it related to each API or resource operation, which is basically a user facing resource operation, so that uh, the service level objectives from the user's point of view are always met. Now we come to the architecture of the multi-cluster monitoring project. So our main objective here was two two types. First is getting an alert for the related SLO. Uh, when the service level objective for a particular operation is not met, we get an alert. And second is to check for any issue or any trend and identify it and add it to our dashboard. So the basic architecture is represented here. As you can see, we have two different type of environments mentioned here, but actually it's more than two environments. We have just shown it as a demonstrative purpose. So we have the Kubernetes cluster, we have hypervisors, messaging queues, as well as a user interface on the production side. We get all the metrics from this from the environments. We push it onto the Elasticsearch or the Prometheus, and then we integrate it all together into Grafana. We also attach Slack into the system, so that if there is any alert, if there is any issue which has to be reported and raised to the developers, then we do it as soon as possible. This is more of the detailed description. So as you can see here, we have added multiple exporters. This is the actual kind of architecture. So there are multiple exporters. For example, you can see that we have an Oslo metrics exporter, which is an exporter used for the Oslo libraries in OpenStack. We have a SS exporter, query exporter. We also have node exporters here, and all of these exporters are integrated together into this dashboard. This is the Verda cluster monitoring dashboard, and the integration is either via Prometheus server or via Logstash and Elasticsearch. And this all goes into the user interface, and we can see this information on the user interface. I will explain a bit more about the exporters in the upcoming slides. Now we come to the monitoring targets. So this is a summary of the targets which we monitored in the cluster monitoring project. So the first is the API. The different APIs which are user facing, we try to monitor them for latency, for the duration of each request response, for the API's health check, and the number of and the success ratio for the API. We also checked the internal components, for example, messaging queue, the hypervisor status, the agent status, etc. We also monitored the physical resources like CPU, memory, disk, file descriptors, and we also attempted to make as discussed, we added the SLO and the resource usage by user. So the resource used by user basically targets or gets the information about how a user or a set of users in a project are utilizing the resources. So if, for example, if somebody is creating and destroying a lot of resources in a short span of time, then that indirectly or directly overloads the system, and that can cause some problems in the uh, cluster in the future, and therefore to avoid that, we targeted the resource usage by user as well. Next we come to the monitoring matrix part, which we have used in the cluster monitoring project. The first one is the user resource layer matrix, which includes the number of VMs, ports, networks, the VM creation time, deletion time, and how we get that information and show it to the user. The next is the API success rate, which includes the API's behavior, how well the API responds. Third is the API response time, how fast the API responds. Fourth is the system resource utilization, like the memory utilization, disk utilization, socket utilization, etc. Fifth is the agent status. Agents, for example, compute agents, network agents, storage agents, how well they are working, whether they are working or not. So an agent normally has three types of statuses, if I can like generalize it. One is an enabled status where it is working properly, so it's enabled and working. The second is a disabled status where this agent has been switched off, so it will not do any functionality. And third is enabled but not working, so that means it's in a failure status. So the status of an agent can be any of these three, and by monitoring the agent status, we can actually identify how this agents work in different, let's say, scenarios. For example, pressure tests, or maybe an upgrade, etc. The next one is the RabbitMQ related matrix, which is basically the messaging queue related matrix. So even though we have used RabbitMQ, the exporters used or the matrix, the way we are calculating it, they can be similarly utilized with other messaging queue applications as well, if not completely, then in principle. For example, with Kafka or with any other homegrown messaging queues. Then we have the API health check. This basically tells if the API is running or not. So it may be possible that the API success rate is not good, but if the API is running, it means that at least that the API is responsive. So the user's request is going to the API. Even if the backend has some problems, at least the API is running. So that is what we get from the API health check. And finally, we have the hypervisor VM load. This is basically telling us the number of VMs running on the system and whether our scheduling algorithm on the compute side is working correctly. Because if the scheduler algorithm is incorrect, in that case, the VMs may not be distributed properly across all the available hypervisors. Then we have the detailed design for the cluster monitoring exporters. This gives us the different exporters, as I explained in the detailed architecture, the different exporters which we have used here. The first one is a query exporter. A query exporter is basically used to run SQL queries on the database and get the data and then expose it on a particular port from where the Prometheus will scrape the data. The next one is a black box exporter. The black box exporter is basically used to probe the endpoints and get the API information. So like the API success rate or the API response time, as he explained here. So the API success rate and API response time, they can be utilized with the black box exporter. Then we have the socket statistics exporter. This basically is giving us a network statistics on the Linux system. For example, the length of the send queue, the receive queue, the network sockets, and those information. Then we have the HA proxy exporter. This basically gathers the HA proxy statistics as well as it provides a basic API health check information, which I have mentioned here. The API health check that can be done by the HA proxy exporter. Then we have the push gateway. A push gateway basically performs batch operations, batch jobs, and this can be utilized to, like, for example, gather some log data or do some processing on the system logs, gather some information, and then push it to Prometheus after performing any particular operation on the data. So, for example, if you want to do push a data onto Prometheus instead of Prometheus pulling the data itself, then you can use a push gateway as an exporter. Then we have the RabbitMQ exporter, which is the messaging queue exporter. It gives us the information like queue size, message size, partition clusters. Then we have the node exporter, which gives us the information about how what are the various hardware statistics and the OS statistics. And finally, we have the C advisor. C advisor is basically gathering the information for the Kubernetes based systems for how a pod is behaving, whether the pod's resources are within the request and the limit parameters or not, and other relevant information about the Kubernetes platform. Then we come to how we are utilizing the multi-cluster monitoring project. So we, as I mentioned, we use it for two parts. One is a troubleshooting and one is a trend monitoring. So quickly going through the different troubleshooting issues. So here we can see like the VM create and the VM delete. VM rebuild operations are not at 100% while the VM delete is. So this gives us a daily, like this is a daily operation success ratio. So by this graph, what I can identify is that the VM delete operation, which has been raised by the user or requested by the user, is working 100% properly, while the VM create and VM rebuild have some issues. So by this graph, we can see that there is a problem at this point or between this point. So we can like analyze the logs at that time and see what was the problem. Next, we come to the agent status. So in this case, I can see that the Nova conductor, scheduler, and console auth, these are compute based agents in OpenStack. So they are all working properly, but we can see that on the Nova compute side, 537 agents have been down at a particular amount of time. And so, again, this gives us a helpful information that these agents were down. So we can just go back and see at that time whether there was any upgrade going on or any other uh, job which was going on which caused this agent going to these many agents going down. And if there was no particular job, it means that the backend failed. But after that, it recovered once again. This way we can analyze how the agents are working. Then we have another dashboard which monitors the control plane health. So in this case, we can like using the C advisor, we can identify if there are certain pods which are failing, if there are certain sidecars which are failing in the Kubernetes environment, and we can showcase it on the system, which can be helpful in identifying how the control plane is actually working on our system. And finally, this slide basically demonstrates how we can integrate Slack into the cluster monitoring system, so that if there is an alert, if there is an issue which comes at an odd time, like at night, then an alert can be generated on Slack, and the monitoring team or any relevant team can be notified about the issue as soon as possible. Then quickly going through the trend monitoring part. So this is basically like the SLO of the system. So in this case, like we can see the weekly average time for VM create is about 38.5 seconds. VM delete is 1.8 minutes. This is an OpenStack system, but these objectives can be utilized with other cloud um, providers as well. So we can utilize this for both synchronous as well as asynchronous API calls and gather the information over a week, over a day, or maybe over 2 weeks or a month, and showcase it for demonstrating the SLO. Then we have the resource utilization. This is the system resource utilization in which we have showcased how like we gather all the data, like the free memory. In this case, we showcase all the pods here which are running. And in this case, if we see that the memory utilization, the free memory goes below a particular amount, a particular target, in that case we change the color. So for example, if we have more than 90% free memory, it's green in color. Something less than 90, it becomes orange. Something less than 50, we can make it on the color, for example, red. It's not here, but yeah, using these color values, we can like check on the dashboard how the resource utilization is going on in the system. And then we have the trend monitoring for the API success rate. So if you can see here, there are multiple colors which showcase that maybe there are more than, because there is an overlap. So there are more than two APIs which are giving more about 100% success rate. Means the request is always providing a proper response, which is an expected response, and not a 400 or 40x error or any other error, uh, which is not within the scope of the user request. So in that case, the API is responding properly. However, if we can see this get method for the slash root, it is going down and it's going almost to 10%, where we have some other API requests again. So what this means is that we can monitor the API, and with this with this graph, I can say that the API actually started to fail, and it did not fail drastically. Like it was not a steep drop, but it was a elongated drop. Not exactly logarithmic, but yeah, uh, maybe it was a gradual drop. What I mean is that the API was started to respond or start to fail as it went along, and then it reached 10%. but not zero at that time. It went to zero after some time. So this may be because the systems are going down gradually, the agents are going down gradually for the get method, or there is some other problem because of which this operation is failing. The main objective of this graph is that by visualizing this, I can say that there was some problem in particular APIs, because of which the cluster started to behave differently. So this brings us to the end of the presentation. The appendix actually includes some other materials which are related to the cluster monitoring project. So if you wish to go through it, then you can download the slides and check it out later on. Thank you and have a nice day.